two particles, A of mass 0.65 kilograms and B of 0.35 kilograms, are attached to the ends of a light, inextensible string which passes over a fixed smooth pulley. I'm going to assume massless. B is held at rest with the string taut and both of its straight parts vertical. The system is released from rest and the particles move vertically. Find the tension in the string and the magnitude of the resultant force exerted on the pulley by the string. Okay, so I'm first going to draw this out. So I'm going to draw the pulley, and I'm going to use boxes just because I prefer boxes to particles, but the concept is the same. So we have one box, which is 0.65 kilograms. We have another one, which is, I think, 0.35. Where did, 0.35, yep, 0.35. And we want to find kilograms, find the tension in the string, and the magnitude of the resultant force on the pulley. So I'm going to just do resultant force pulley. Okay, I'll finish up the line. Okay. So the idea here is we have two forces. We have, I'm going to call this force gravity A, and we'll have this one right here, I'll call this force gravity B. And they pull down on each other. And we can, if we wanted to, there's two common ways of solving this problem. The more formal way I'll show you first is like this. So this is going to be tension. I'll call this tension A. Then there'll be this, tension B. So basically, if you look at just this block B in isolation, you're going to have gravity pulling it down, but you're also going to have this tension in the string pulling it up. And that will affect or mitigate how fast it falls. So normally if something falls, it falls at 9.81 meters per second squared. But when there's a string pulling it up, it's going to slow it down a little bit. So if we look at these two systems in isolation, so we'll look at A. So we know that it's always true in life, or yes, it is true in life that the sum of all, no, that's a terrible summation tool. There we go. Summation of all forces will be mass of the system times acceleration. And in this case, the sum of all forces will be force gravity A minus tension A, okay? And then I can write this again at the force gravity as mass of A times gravity minus tension of A. We'll do the same thing for B. So this will be mass of block A times acceleration of A. Okay. And then we do mass of block B times acceleration of B. The acceleration of A and B will be the same because they're attached by a string which is taut. Taut meaning it's no slack in it. Tight. So force gravity B minus tension B. So I'll do mass block B times gravity minus tension B. Well, this is all the same string. Since it's taut, we'll also know that tension A equals tension B. Whoop, like so. So what we can do then is we know that the acceleration of both blocks are the same. We just assumed that the two tensions are the same, so I'll erase this part right there. And now we can solve for the tension and plug one system of equations. So this is our system of equation for B. This is our system of equation for A. We can solve for tension and then plug that one equation into the other. So I'm going to solve for the bottom one. So we can say that tension, this tension here, equal, ooh, wait a sec. Sorry, one thing real quick. This is going to fall downward, and this one's actually going to go upward. So this acceleration here, it's actually going to have a negative sign in front of it. Because block B is going to be moving up, block A is going to be moving down. So the accelerations, even though the magnitude is the same, the directions will be opposite. Okay, so I'm going to take this equation, solve it down here. So we have mass block B times gravity plus mass block B times acceleration. This will be, Yep, and I'll just leave it like that. I won't simplify it. So now we're going to plug this into this equation right here. So we have, let's see here, mass block A times acceleration equals mass block A times gravity minus, now this is going to be minus this tension up here that we just solved for using the second equation, mass block B times G minus mass block B times A. We're trying to solve for A here in this equation. So I'm going to move all the A's over to one side. So we have A times mass A plus mass B equals gravity times mass A minus mass B. Then one more solving, we have A equals gravity, mass A minus mass B, all over mass A plus mass B. And then plugging numbers into this, A was 0.65 and B was 0.35. So we have gravity, which is 9.8, 9.81, 9.8, similar. So we have 0.65 minus 0.35 all over 0.65 plus 0.35. So on the top we're going to get 0.3. So 9.8 times 0.3 all over 1. And looking at our calculator, on 9.8 times 3, we get 29. Let's try that again. 9.81 times 0.3. There we go. 2.943. 2.943 meters per second squared. Now, that's most of the way to the answer, but it's not the full answer because we need tension. So we'll go back up to this equation right here where we solved for tension. We need to solve tension for B, but tension's the same for A and B, so it doesn't matter which one we do. And let's see, I'll do green. So this will be then mass B, which is 0.35. 0.35 times gravity, which is 9.81, plus 0.35 again, times acceleration, which we just found, which is 2.943. 2.943. And we should get, add this to 9.81 times 0.35, and we get a tension of 4.46. 4.46 newtons will be the tension in the string. So that is the tension in the string right here, 4.46. You write each block in terms of tension, and then from there you can solve for the acceleration, and that acceleration you can then backtrack into tension. You could probably solve for tension the first time without going through acceleration, but usually things are going to ask you for acceleration, so that's just kind of the method that I've learned how to do this. Okay, that's the more correct, more formal way of doing this. A less formal way of doing this is go back to sum of all forces equals mass times acceleration. So this is going to be mass total. And these are net external forces. So I'm going to say the first force is going to be force gravity A plus force gravity B. Well, the mass total here is going to be mass A plus mass B. So this is going to be mass A plus mass B times the acceleration of the system equals force of gravity A, which will be mass A times gravity plus mass, minus mass B times gravity. And the reason I had a minus there is because even though they're both acting downward, this string is causing them to basically oppose each other. So they're working against each other destructively as opposed to constructively. And that's why I have this minus sign here. And then if you solve it, you get acceleration equals gravity mass A minus mass B all over mass A plus mass B, which then gives us our same equation we had right down here. And we just basically skip this whole systems of equations thing. So depending on how much time you have, which is probably not a lot, you can do it through either this method or that method with tension. I prefer this method, just looking at net external forces and then solving for acceleration that way when possible. It's good to understand both methods, but when you're in a timed evolution, I find this method preferable. So now, to find the resultant force exerted on the pulley by the string, we'll look at it right here. Let's do green. I think it's the force from the string pulling down the pulley right there. And so the way I would approach it, my guess is that it's just going to be the sum of the two tensions, since they're both vertical. And since both tensions are the same, they're both 4.46, the tension on the pulley would equal, 8.91? I think that's right. 8.92, this number times 2 newtons. That's how I would approach this problem. I think you might hear it sometimes referred to as an Atwood machine, where you have two blocks sliding up and down. So I hope that helped kind of get the concept, and see you next time.